So, can you all understand me? I guess you can. And have you ever wondered why you can? Why is it so easy for humans to understand spoken language? Or to put it in a different context, why is it so hard for computers to do a thing that is so easy to us? So let's talk a bit about how speech recognition works in computers. Or the question, the statement, let's file the linguist. You're going to find out what that means. So before I actually start bringing you into the topic, I want to show you how we actually want to interact with computers.
1974 Stark Expo model scan complete, sir.
How many buildings are there?
Am I to include the Belgian waffle stands?
That was rhetorical. Just show me.
That would be nice, wouldn't it? I think reality looks more like this.
Computer? Computer? Hello, computer.
Just use the keyboard.
Yeah. So I think every one of us has such experiences with computers not working, not doing what we want them to do. Why is it so hard in speech recognition? What is so hard detecting a speech signal and the words being spoken in it? Well, have a look at this. This is the waveform of spoken language. Can you guess from just looking at it what it says? Not really. That's me saying Science Slam. It's quite easy once you know, right? Because you see this and this part, that's the S, and so on. So how can we make a computer understand that? Well, first, let's see what we're going to want to achieve. We have a speech signal, which we call X, and we want the word sequence W that is being said in X. Why is it called X? I never actually dare to ask, but I explained it in this way. X usually is the free variable, and it stands for speech, so X is, so to say, the freedom of speech. How do we do that now? We apply math to it, as always. We just use statistics, actually. That is the fundamental equation of speech recognition. You all knew that, right? Yeah, I thought so. So what you actually want to do, we have a speech signal here. Oh, it's really like hard to do that. Speech signal here, and we want to get the W, our word sequence out of that. So we have want to get the probability, the highest probability of a word sequence given a speech signal X. And we can decompose that, for those of you who have done a bit of statistics, using the Bayes theorem, using this right-hand side of the equation. Basically, we just switch those two variables, so we get the probability of speech signal given a word sequence times the probability of the word sequence itself. We won't talk about this part down here. That's the a priori probability. That is not too important. We don't need that. But we're going to learn a bit about why this is called the acoustic model and why this is called the language model. So let's jump right into it. How does a computer do that? Of course, computer scientists always have block diagrams. This is kind of a flowchart thingy. We start with our speech signal, do some pre-processing. Hi? Oh, still working. Pre-processing, because we just learned just from the sound waves, it doesn't work. So we need to apply some more stuff first, and then we got feature vectors, which is nothing else than just numbers, basically, math, boring. And put those into our models that we just saw, the acoustic model and the language model. Then magic happens, and we get the word sequence. Cool. That's easy, right? So let's do that in practice. We do the pre-processing. We have our speech signal saying Science Slam. What do we do now? We extract features from it. In this case, we use the spectrogram of it, which is the frequency of stuff being said in here over time. So basically what you can see here, let's go down a bit. What you can see here is frequency in short amounts of time of this signal. So up here in the diagram, you see stuff that has a high frequency. This is dark and high in the diagram, so high frequencies are quite much here, as in this part or this part here, which is the S, because that has a lot of high frequencies. Whereas this part here, which is the A of slam, that is low, so you have the dark part down here. So that is our first step. We now have single feature vectors, just the columns of the matrix, math again, and numbers, and we put them back into our models here. So that is actually how we all start with that. So let's talk a bit about the acoustic model then. How do we do that? Well, as we just saw, we have the dark part here standing for an S and the part for an L and A and M and so on. Once you know that, it's pretty easy to see, right? Actually, there are people who can read those diagrams just by looking at them and say like, well, this is clearly Science Slam. I'm not joking, it's amazing. And if people can do that, then computers probably can do that as well. Maybe, hopefully, that's the goal. So let's see how that works. We take those feature vectors and see what most probably is in them. So how do we do that? We have a lot of training data, let's say a couple of hundreds of hours of speech, just people talking. And we annotate that frame by frame, like millisecond by millisecond, or 10 milliseconds by 10 milliseconds, and say, at this time there's an S. Next time, still an S, still an S, still an S, and so on. And then suddenly there comes an L, and we have the annotation L. From that, we let the system just crunch all the data and learn like an S typically looks like this. An L typically looks like this, an A typically like this, and so on. We do that for all the different sounds there are. Usually in English language you would use something like 50 different sounds, so little bits of sound, and you can distinguish in beginning, middle, and end part of the sound, because a K, for example, is like it has this explosive K in the beginning and then the A in the end, so you can put that into 3 different parts to make it better for the computer to understand Ks, and so on. So we have all this data, and then we can loop through our states here. For those who have worked a bit with automaton theory, this is a Markov chain. Pretty cool. And it is. And we don't know the states here, so we actually have to guess, like from the looks of the stuff down here in our feature vectors, we have to look what's in there. That is most probably an S, and that is most probably an L, just derived from the training data that we saw. So in practice it looks like this. We have different sequences of acoustic segments, and we just see which one of those and all the other possibilities is most probable. So we just try out everything, like this is most probably an S, maybe 80% an S, 20% an F or so, and get a sequence of acoustic short segments. But that is just half the stuff, because now we have a sequence of acoustic segments. That is not a whole sentence. We don't want to have that. We want to have the whole sentence. So we need to apply some model for the language as well. What is the language model for then? Yeah, well, we just want to turn those acoustic sequences into proper good sentence. So what the language model actually is trying to tell us is what is a good sentence and what not. For example, the probability of the sentence correct horse battery staple is meh, whereas the probability of make me a sandwich is of course yay, because that's a good sentence. So how does that work? We take the sentence and decompose it even further. So we just multiply different probabilities. I took 2 words at a time here. You can also extend that to 3, 4, or even 5 or whatever words in a sequence, and assign single probabilities to them. So this first one would be the probability make being the beginning of a sentence, then the probability that make is followed by me, and so on until sandwich being the probability of like the end of the sentence. Once you have that, you can multiply that and get the probability for this whole sentence. How do we get those numbers? Again, we use data. So we take a lot of text and let the system crunch the data. And then we just count how many times did we see make me just up one after another, 6 times in a text, make all 3 times in a text, and so on. And for example, if you would have a text containing lots of cooking recipes, probably the probability of sandwich would be higher than if you take legal documents or so on. So it also depends a bit on your context of the data that you put in there. But pretty much it's all just counting and numbers. So what we have done now, we have our probability for the acoustic model from how probable is it that this thing is actually an A, an L, and so on, and the probability of our language model saying this is a good sentence, this is not. We don't need this part, this is not important. So from those, it actually isn't, so usually it's just dropped. So yeah, it's no joke, we don't need that. We can multiply that and get the most probable sentence from that, which of course in this case will most definitely be Science Slam, because that's what I said. So what you just heard was kind of the basic introduction to it, but did you realize one thing? I didn't never talk about the language that was in there. So how does that work? We just take data, no language in there. We just use sound data, we use text data in the language, of course, that we want to learn and that we want to recognize, but still there is no linguist, no linguistics in there, which led a famous researcher in speech recognition say this thing. Every time I fire a linguist, the performance of our speech recognition system increases. Which basically means I think the official interpretation is something like, it's just math, but you could also say, linguists are really suck at recognizing speech. Hope you learned something today. Thank you. Oh yeah, questions?
Thank you, Lucas. Thank you.
Sure.
Do you have any questions for Lucas?
So are there better feature vectors than the spectrogram?
Of course, there are many more features that are just needed to simplify a bit. So you can also use the spectrum of the spectrum, which is called the, wait, what was it? Capstrum. So actually you use spectrum and just flip the first 4 letters. And then the frequency that you get there is not frequency, but frequency, for example, which is funny. Just switch the first 4 letters. You can use different deltas of your frames, like look at the frames ahead and back and stuff like that. So this is kind of an art in speech recognition, finding the right features. So you just take, basically what it is, it's just lines of numbers, right? And so you can put in anything in you want there and just let the system learn what an A looks like or an S or whatever, just given those numbers. And what numbers you plug in there doesn't really matter. As long as they're good, it works. And there are many possibilities to do that, of course.
I've got 2 for you.
Sure.
Okay, so the question is there a computer big enough to decode the New Zealand accent?
Well, it's not a matter of computer, it's just a matter of training data. New Zealand has 4 million inhabitants. If you let them speak like every one of them for a minute or 2, then you would have enough data. So it's just a matter of collecting enough data, and then you can train any system to do New Zealand accent as well. That is not a problem. I'm not sure if everyone has done it yet.
Hi. My question is, like, every time you are using any application which is recognizing only a pattern which is only few accents, which, for example, Siri or Google Voice recognize 100%. So far, as I say, still is not 100%, I believe. At the same time, I want to ask you a question where as you said, linguistics, it's a big information to have where a computer can understand. Example is, as Paul said, a New Zealand accent, and I would say Indian accents, and so on. A
Wait,
German
sorry,
accent, maybe.
Can you shut up? I don't get the question if you're all talking.
The question, in general, is it the way in the future to know all the accents, and when you start to speak with a computer, it understand you 100%?
Well, that would be a great future if we could do like a speech recognition that is independent of an accent or even independent of the language. That would just go like, wow, cool, that is Spanish. Let's recognize Spanish now. That would be cool. I think we're kind of far away from that now, because once you plug in too many different languages, accents, or whatever variants, of course, the recognition errors increase, because the system isn't then too sure. Is that now just a word in this accent, or is it another word in another accent or language, and just starts confusing things. In the future, I hope it will be possible, but for now, I think not really.
Is it a probability formula that you have where it's
for accents,
calculations are done for speech recognition?
You mean, oh, yeah, that is not anymore on there. You mean this formula?
Yeah. Is this the only formula?
Well, that is the most important, but of course not, no.
Okay, cool.
Well, you can, like, for all the different models, they have all their own mathematics behind them and everything, so there's a bit more, but 10 minutes are just not enough to explain that. If
Any modulation included in that?
Modulation?
Of frequency? Modulation
what do you
included?
mean, like your voice level and pitch and stuff?
Yeah.
You can definitely make features out of those. Yes, you do that. Like, you can just say, like, usually the bass frequency of your voice, like male have a bass frequency of like 120 to 150 hertz, females 200 and 250 hertz, stuff like that. That is already taken care of. So that is done in the pre-processing as well. And you can also, for example, use those stuff to recognize is it a female or male speaker and stuff. That is already being done, yes.
We still have 2 questions. I just want to remind you that you're all free to discuss anything you want with the speakers after the talk, but we're just going to take a couple more questions now.
Yeah, I'll be here, so later.
So can you apply your method to brainwaves?
Of me saying Science Slam?
Can you apply this to brainwaves?
Brain waves. Oh, I never tried, I don't know. How do you get brain waves? Like just EKG or so? Well, a friend of mine actually worked on something similar, which was using the muscle voltage to recognize speech. So he would put electrodes in his face and just speak silently like this and try to recognize speech from that. That is pretty amazing. So he was quite successful with that, actually. You can do that. Brainwaves, I don't know. Maybe.
See, Science Slam gives you ideas.
Yeah. Well,
Okay.
I'm not working in that field anymore, so...
Yeah, well. One last question.
Very nice talk. I just had a quick question. So you said, depending on the features that you train, the context of the training that you do, you get different probabilities for different sentences and different words.
Yeah.
How do you select a training set that's general enough so that you don't have any biases in your predictions?
That's a good question. So there's another famous quote in speech recognition which goes like, there's no data like more data. So basically what you try is to get as many data as possible, speech and text and whatever. Also, if you're trying to develop a speech recognition system for general use, it's really hard to do that. So the good recognition systems that are out there today, they're basically just limited to different domains. Like there's stuff for lawyers or doctors or stuff that is trained on those words and those phrases that they use and stuff like that. The more general you get, the worse your recognition accuracy gets. So still something to go. I think one solution is just use more data, so you can never have enough, and maybe you'll never have enough if you still use this technique. Maybe that we need other techniques like super intelligent, artificial intelligence stuff that can do that without the math, without us knowing what the math behind that is. So far it's just more data. That's the solution.
All right. Thank you, Lucas.
Sure.